Hey class, I wanted to talk a little bit about the mean value theorem. You do have, I think I assigned like 2 questions from WebAssign on this. It's not something you need to, that's vitally important, but yeah, there's one of these questions on the practice exam. Of course, I wanted to talk a little bit about it because this is another theorem which, in my mind, is sort of like a common sense thing, but this one's a little less of an obvious trait. But once you kind of get it and think about it, it makes a lot of sense. So let's just take a peek at what we call Rolle's theorem and the mean value theorem because they are very interrelated. But Rolle's theorem says let f be a continuous function that satisfies these 3 hypotheses. 1, f is continuous on a closed interval. It's differentiable on that open interval, excluding the endpoints, because again, endpoints may or may not be differentiable if they are not smooth. And then number 3, f of a is equal to f of b. It says if those 3 things are true, it says then there is a number c in AB such that f prime of c is equal to 0. So this is actually equally, if not more important than the mean value theorem. But let's try to draw an example and see why this may make sense. So what it's saying is that first of all, it's continuous and differentiable, meaning another way of thinking about that is it's smooth. It doesn't have any weirdness on the graph, no holes, no asymptotes, none of that. And number 3 is kind of the important, not that 1 and 2 aren't important, but number 3 is sort of getting at what it's the importance of the theorem. But it says f of a must be equal to f of b within those hypotheses, meaning like the endpoints have an equal position. And the endpoints aren't so much important. All it's saying is that, it has the same y value at a particular point in time. Sorry, I did not mean to write that. Let me try to use my stylus here. But let me draw an example. So say we have, here's our graph and, we have a function, whatever, like this. What it's saying is that if there's 2 points on the curve where it has an equal height, so let's just say, I don't know, right here and here. Like these 2 positions are A and B on this function, where the y value is the same. Sorry, not my best drawing effort. What it's saying is that in between the interval A and B, there has to be a critical value. There has to be a point at which the derivative of some position C is 0. And notice that, in between A and B on this random thing I drew, there was a position that had a horizontal tangent line. So noticing within the interval, there had to be some horizontal tangent. Basically, what it's saying is if the curve has 2 equal positions at the start and the end of the interval are equal, there has to be a critical value in between. And this is very important for the min-max principles that we covered in our videos from Monday. But why? So what is the common sense here? But basically, if it kind of goes back, if it's the same y value at the start and the end of the interval, what that implies is it has to go down and come back up, or go up and come back down, right? Because in order to maintain a level, it either has to be completely flat throughout, or it has to change from increasing to decreasing, or vice versa. So basically, what it's saying is there has to be a min and max if on an interval it returns back to the same value. And again, it's kind of common sense because it's sort of like along what goes up must come back down. If it goes up and comes back down, then there has to be a min or max somewhere in between. Again, if it were not continuous though, or if it had other calculus-based issues of smoothness, this may not be true because again, asymptotes mess with these sorts of things. But the continuity, it only works with continuous functions, much like the other properties. So if you have a discontinuity in your interval, you can throw that out the window. Mean value theorem is almost exactly the same. However, how I think about this is Rolle's theorem says that in between 2 positions, assuming they're equal, it has to have a derivative of 0. Mean value theorem is kind of the same thing, but generalized a little bit further. Let's go ahead and look at it and try to think about what it's saying. It says let f be a function that satisfies the following hypotheses. 1, f is continuous. 2, f is differentiable on the interval, same deal. And then the remaining part is what's different, of course. Then there's a number c in AB such that f prime of c is equal to f of b minus f of a over b minus a, or equivalently f of b minus f of a is equal to f prime of c times b minus a. So I prefer to look at number one, but these are of course the same thing. Just one is solved for f of b, minus f of a, and one is solved for f prime of c. But what this is saying is how I look at it is what it's saying is the derivative at c is equal to the average rate of change across the interval. And looking at a graph can make a lot of sense about what this is really saying. Because, if we look at the blue line on your notes, I know your packets that I gave you guys are not in color, but the bottom line is the secant line between A and B, right? The secant line is an average slope between 2 points, which can always be calculated by delta y divided by delta x. However, a tangent line is dy divided by dx. It's the instantaneous slope at 1 point. And as we all know, that's the derivative. The derivative gives us a slope at an instantaneous point. What this is saying, what the mean value theorem is saying, is that the slope of a tangent line is equal to the slope of the secant line between the 2 points somewhere in between the interval. And C, it's kind of like with the mean value theorem. We don't really know where the min and max would have been in between the level, but we know there has to be a min-max somewhere in there. Similarly, this is the same thing. We know the secant slope between the 2 points is this. Somewhere in between, it will attain that as well. And so, say I take that same curve and I was to try to explain, the sense of the mean value theorem instead. Well, instead of having to pick 2 points with equal A and B's as we have to with Rolle's theorem, we can pick any 2 points on the curve at all. So let's just say I pick those 2 points as my A and my B on whatever random curve I just drew. If I draw the secant line that connects those 2 points, it has, a very particular slope. What it's saying is in between A and B, there has to be at least one position, C, and again, it doesn't specify there has to be only one. There could be more than one, but there has to be at least one C value in between that has the same slope. And notice if I'm looking at it, how I would visualize it is I would look for, well, can I connect a parallel line to that graph somewhere? And notice like right about here, it appears the slope of a tangent line there would be equal to the slope of the secant line. And, again, what you kind of, if you're trying to visualize the mean value theorem, we're looking for a parallel line to the secant line somewhere in the curve. And it must have it. So what I want to say is, well, why? Because, again, you can look up the mean value theorem in the proof. The mathematical proof exists. I don't want to get into that in this video. But why? And how can we understand why this is true? But if you think about it, right, if we're traveling between 2 points on a curve, right, like looking at this example, it starts by going down. The slope is a lot less steep in between those points, right? If we kind of think about the tangent slope at the start, it's going to look like this. The tangent slope at the end is going to look like that. And if we have to get between them, I'm kind of imagining, the slope is starting like this, and then it's turning around and going back to this. Over the course of it, again, assuming it's smooth, continuous, and differentiable, the tangent line can't have any weird leaps, because if it's not different, the differentiable condition is important here, because if it's not differentiable, the tangent slope could be really wonky. But basically kind of what I'm imagining is the tangent slope starts at one position like this, and then it has to gradually change to the tangent slope at the end. And if you kind of look at those two slopes, somewhere in between, it has to make the secant slope. So notice the secant slope is sort of like an average slope between those values. Again, it's not exactly the average of the individual tangent slopes between them, but this intermittent point is somewhere in between. And kind of as we're progressing through the curve, we can imagine the tangent slope changing as we turn around. It's kind of going from decreasing to increasing. Again, notice there would be a zero in between there. It doesn't have to have a zero based on these conditions. But what it's just saying is that the slope of the secant line has to be attained somewhere in between on a tangent. Very, very similar to that idea from Rolle's theorem. So what would a homework question look like? Or what would a test question look like? Let's just peek at the example from our notes and work through it. So, this example says let f of x be equal to x squared. It says find the average slope on an interval. So, again, this would just be another way of saying find the average rate of change where, we've got A and B. So how I like to do it in class is, we'll just write a formula. A or C equal f of B minus f of A over B minus A. And so, well, f of 3 would be 3 squared is 9, and minus negative 1 squared is 1. And, of course, minusing a negative is plus, so 3 plus 1 is 4. So what we'd end up with is 8 over 4, or 2, as the average rate of change on the interval. And if we create a little sketch of this, actually that's what the last part of our question is saying to do. Let's just go ahead and, well, we have a basic parabola with a vertex at the origin. And if we're looking at, from negative 1 to 3, the slope of the secant line, that's what we'd have here. We have a slope value of 2 between B, A and B. And what it's saying is that between, if I'm looking at Rolle's theorem or the mean value theorem, well, Rolle's theorem is not applicable on this interval because f of A and B are not equal. And again, that's kind of the key difference here. But imagine we took a level position across a horizontal line intersecting with the parabola, then we could apply Rolle's theorem instead. And of course, we can see there is a minimum, of course, in between any level of the parabola. But again, the mean value theorem is a little bit more, it's like a generalized Rolle's theorem as far as my brain remembers it. But anyways, notice again, if we're traveling through the slope, this slope is 2. What it's saying is somewhere on the curve between the points, it has to also have a slope of 2. Again, if I'm imagining a parallel line, notice I can kind of see, there is a position somewhere on here that has a slope of 2. Now, I could try to figure that out with the graph, but we know we could do a derivative and figure out where that is by the derivative. And it says, the next thing on our notes, say explain why there must be a C value where f prime of C is equal to 0. Well, if I apply Rolle's theorem, let's just say between negative 1 and 1, because both negative 1 and 1 squared are both equal, there will be a min-max in between any symmetric points on the parabola. More complicated is explain why there must be a different C where f prime of C is equal to m. And since this is not 0, we know that that point is not the min-max, right? So for the mean value theorem, it's got to be a different location. But yeah, this would be the mean value theorem. Sometimes I've seen people just write MVT as a shorthand for mean value theorem between negative 1 and 3, because we know that the slope of the secant line between negative 1 and 3 is 2. The mean value theorem says there is a different position C, which is what I've drawn here, that has a slope of 2. But we don't know what C is yet. But if we take a derivative, we can solve it. It's very simple. So f prime of x, as we know, derivative of a power function, we can drop the power and subtract 1. So derivative of x squared is 2x. We've done this by difference quotient as well. And if we want to figure out where it's equal to 0, well, we could solve the critical value just by taking it and setting it equal to 0. So, as we know, the critical values indicate where the mins and maxes are. That's, of course, going to be at x equal to 0, the vertex, as we all know. The mean value theorem is a little bit more interesting, but it's very similar. Instead of taking your derivative and setting it equal to 0, you want to take your derivative and set it equal to m, because that's what the mean value theorem says, right? The mean value theorem says f prime of C is equal to ARC, the average rate of change. So if we just take the derivative and set it equal to 2 instead, so what we could do is take f prime, set it equal to 2. We'd be looking now for where is the slope to, and this is going to give us C. So basically this will be C, but I could call this f prime of C if I wanted to. I'm just going to leave it as x, because we know that f prime of x is 2x equal to 2. And what I could figure out is x equal to 1 is the location where the slope is 2. And so this is going to give us our C value for the mean value theorem. It's that intermittent point. Here it just so happens to be halfway in between. That's a coincidence. That will not always be the case. It's not always going to be right in the middle of the interval where the slope attains. As like if you're looking at this graph, it kind of looks the same where the intermittent value, the slope of the tangent attains the slope of the secant halfway in between. Again, it's not always going to be halfway in between. Like in this graph here, notice that it appeared to have attained its tangent slope nowhere near the middle. But anyways, obviously we can always solve it. My point is you can solve the point by taking the derivative and setting it equal to the ARC. It's kind of similar to taking the derivative and setting it equal to 0, where taking the derivative and setting it equal to 0 will give you the min-max. This will do something else. Again, mean value theorem, quite useful. It's important actually for establishing the integral, which is what we're going to get into in chapter 4 in a couple weeks. Anyways, that will wrap up this video.